today and Monday, we're going to look at both exponential models and logarithmic models. So today we're going to spend time just talking about exponential growth and decay models. And notice that you have two different formulas for exponential growth and decay. One uses the base of e, and one uses a regular number. Either b is bigger than 1 if it's a regular number. I didn't mean that. I meant it's not e. It's not an irrational number. B is, if b is greater than 1, we know then it's going to fall under the exponential growth. And if b is between 1 and 0, we know it will be exponential decay. So these two formulas are equivalent. And in order to make them equivalent, we either set b equal to e to the k, and you can see that if I replace b with e to the k, they're exactly identical. Or if I replace k with the natural log of b, they're also identical, because e to the natural log of b, remember, is one of the properties where we compose our two inverse functions and we come right back to b. So this is equal to a sub naught b to the t. They're totally equivalent. And these two equations here you'll be using throughout your first activity today. If you know k, then you can find b by saying e to the k. That gives you the value of b, which is your base for this exponential here. And if you happen to know b, but you don't know the continuous growth rate k, you can find k by taking the natural log of b. So sometimes students like to see, I know some of you don't really care, but let me show you how you can go back and forth between these two formulas and see this relationship. So just as an aside, you don't even have to write this down if you don't want to. I'll never ask you to do this. So here's the first equation, a sub naught equal times b to the t, and we're saying that these two models are equivalent. So as you know, you could divide both sides by a sub naught, and that would give you a 1. And here you have b to the t equals e to the kt. Okay, and we could take the natural log of both sides. So if we took the natural log of both sides, we use our log properties. The t is going to come down in front and multiply the natural log of b. And now on the right-hand side, the kt comes down in front and multiplies the natural log of e. Well, what's the natural log of e? 1. So this is a big fat 1. So we get t equals the natural log of b, and that's supposed to equal kt. If you divide both sides by t, you get the natural log of b equals k. So that's just to show you how you can work from one formula to the other and get if you happen to know b, you take the natural log of b to get k. So if we scoot right over to your exercises for today, this is one of your exercises right here. And it's your first exercise. And notice here that you're given either the annual growth factor b, or you're given the continuous growth rate k. So if you know one, you can get to the other. So we know that k is equal to the natural log of b. So here's b right here, and the first one for the United States. So to get k, we would just take the natural log of this number, and we would have the continuous growth rate. Down here for China, we have the continuous growth rate. So to get the annual growth factor, to get b, you just take e to the k. So you can move back and forth between these two columns and then use either model, rewrite the population growth rate using either model here. So that's what you'll be doing in about a half an hour. Okay. So one thing I want you to pay a little bit of attention to is Qatar. Anybody know where Qatar is? Yeah, Chris? It's off of Saudi Arabia, right? In fact, it's a little teeny peninsula, and its area is only about roughly 4,500 square miles. And look at China's area, 3.7 million square miles. Very small. And the reason I want to, I'm showing you this in terms of the area of these two countries. So later on, when you're looking at the graphs for this learning activity, I want to show you something about it, which is just impossible to happen. So anyway, but when you look at this activity here that we were just taking a look at, and you look at the growth factors right here, what you usually see reported in the paper or a magazine or anything you're reading is you don't usually see the growth factor. You usually see a percentage, like a growth rate. So if you were looking at the growth rate of Qatar, the growth rate of Qatar is the growth factor, this thing, 1.112 minus 1, because the 1 in front just represents 100%. So the growth rate is this, 0.112. That's the growth rate. This is the growth factor. And what this says is that the population of Qatar right now is growing at 11.2% annually. That's amazing growth, because so right now, if the population's 1.7 million in 2010, that means next year you're going to have 11.2% of that population for the next year. It's directly proportional to the size of the population. That's why exponential growth increases so rapidly, because it's directly proportional to whatever the size of your population is. So that's just a little side. This little thing is usually what you see reported. It's called the population rate, and you just change it to a percentage, 11.2. So if you look at the United States, what would be the growth rate of the United States? If the growth factor is 1.00969, what's the growth rate as a percentage? Yeah, 0.969%. So it's actually less than 1%. So we're not growing very much. Okay, so you can kind of look real quick at each of these countries and see what the different, when you have the growth factor. Now, for these countries, you'll have to convert it back. Okay, or actually, this is the continuous growth rate. So let's see. Let's go back. I just wanted to point that out, that that's where we're going today. So all these different variables stand for different things in the context of your problem. A sub naught is just the initial amount. And often when we're talking about populations, they would put P sub naught here. That's often your population model would look like this. The population at time t is your initial population times b raised to the t power. And again, if you had a continuous growth rate, you would use this instead. So we just changed the little number, this little variable here. Sometimes we use a sub naught. Sometimes we use m sub naught for half-life, how much of the initial mass you have of a particular element. Population p sub naught. Okay, so that little variable changes depending on the type of problem you use, but they all mean the same thing. They're all the same formula. Okay, and as I mentioned earlier, with interest, right? The amount of money you have over time is P e to the RT. Remember I mentioned that formula PERT, which some of you hadn't heard of. So it's, again, all of these models here are interchangeable. So let's take a look at this Ebola outbreak, and thank you, Andy, again. He gave me this data for the linear regression project, and he noticed when he plotted it that it was an exponential growth function. And so I used the data he gave me to get this problem for us today. So you want to read it, Andy?
Sure. The Ebola outbreak in West Africa. On September 3rd, 2014, there was an estimated 2,902 Ebola cases reported in West Africa, Guinea, Liberia, and Sierra Leone. Between September 3rd, 2014 and November 18th, 2014, the number of Ebola cases grew at a continuous rate of 1.252% a day. Sources: World Health Organization.
Okay, so what we want to do is we want to construct two equivalent models. One using this first model where we don't have the continuous growth rate, and the other model is where we do have the continuous growth rate. So right now, we can immediately go from this language to this model because we know the continuous growth rate. That's the value K. That's what K is. So right now it's given as a percentage. So for your model, you have to convert it to a percentage. So K equals 0.01252. So if I were trying to write a model that I could use to try to predict the number of cases over time, either outside of November 18th, beyond November 18th, or sometime in between September 3rd and November 18th, K would be equal to 0.01252. So I've got that value for my model, 0.01252 times T. So what's A sub naught going to be here, or P sub naught, or whatever we want to call it? What's going to be the initial number of people that were infected with Ebola on the day we started recording this information? Right, 3,902 is your initial number of people that were recorded with Ebola on September 3rd. So 3,902, right. So that's the model we could use if we use the continuous growth rate. Okay, and again, when you read a problem, you have a choice between these two models. You don't have to do all this like conversion. If you're given the continuous growth rate, then use the model with E as the base. It's straightforward. You just plug in your numbers. However, I do want you to see how you could go from this model to this first model, this exponential growth model. So in this model, we know K. In this model, we have to find B. And to do that, to find B, we just say B is equal to E to the K. Because if you look at these two models right here, this quantity has to equal this quantity. That's the A sub naughts are the same and the T's are the same. So B must be E to the K. So since we know K, we can find B. So let's find B. To find B, we say B is equal to E to the K, which K is 0.01252. So we can either use that like that, or we can get an approximation as far as we can go with our calculator, number of decimal places. So let's see. B is going to be equal to E to the K. So let's turn it on. E to the X is right here. It's the inverse of the natural log. So it's the little yellow E to the X above the natural log. So E to the 0.01252 is B is equal to 1.012598703. So my model here would be F of T equals 3902 times 1.012598703 to the T. Now what I wanted to show, what I showed my students in the first class is, this is an approximation for B. Here's the actual value for B right here. This is the actual value. So if you wanted to use you want to get the most accurate answer here, you would put this entire number into your calculator as the model. And the way to do that is, since this is just an estimation of E to the 0.01252, is you can actually store that information. And one of my students said I made his day in my first class when I showed him this. So let's say E to the 0.01252. If you want to get that exact value for all of your calculations that you're going to do, you can store that in your calculator with this little button right here that says STO, and it has a little arrow here. So I'm going to store it, and the way you store it is you can give it a name, or you could just assign it a letter. Well, in this case, the letter that it's representing is the base B. So I'm going to give it the letter B, and the way you do that is you hit alpha, and then notice B is right here, alpha B, and you hit enter. So now whenever I want to use this model to find a particular value for a particular time, I just use the letter B, just like it is in here. So let's take a look. I decided let's be current, and we know that this model is for the dates September 3rd to November 18th. That was the last date that the Ebola cases were counted. in West Africa. So if that represented the 83rd day, and we wanted to know how many Ebola cases would be predicted using either one of these models. So let's take a look. The first model was 3902 3902 times 1.012598,703, which I have stored in my calculator, stored under the letter B in my calculator to the T. That's one model. And our continuous model was f of t equals 3902 e to the 0.01252t. So if I want to figure out how many actual Ebola cases would be recorded today, December 5th, 2014, I'd have to figure out how many days today is from September 13th. And it's 100. 100 days. So t is going to equal 100, the value 100. So I put this into my first model. And I'm going to use the big letter B because it's easier to write in my, we'll get it out of my calculator. And in our second model, we put 100 in for t here. So let's take a look at what we get. So since I've stored this long number in as B, I'm going to say y equals 3902. Oh, thank you. 02 times E. And now I can actually write the value B by saying alpha. Oops, sorry. I'm getting ahead of myself. Let's do the first model. 3902. B is stored in alpha B raised to the X. Okay, so there's my first model. My second model is with the continuous growth rate is 3902 times E raised to the 0.01252 times X. Okay, so these two are equivalent. So now when I set my table and I say, let's take a look at day 100 and incrementing by 1 day at a time, they should be exactly the same. So here's day 100. It's predicting both of them. Notice how the numbers are all exactly the same to show you that the two formulas are equivalent. So it's predicting that today there would be 13,647 cases recorded after 100 days. So on December 5th, 2014, there would be an estimated 13,647 Ebola cases in West Africa. So we're using this model to extrapolate out to today because the model was only good for the data up to November 18th. So I asked Katie and Isabel and Megan if they would try to find an estimate or a prediction for right now the number of Ebola cases in West Africa, and that's what they came up with, 17,256. So they looked that up. What did you use for your source? CDC. So that's the Center for Disease Control. And so you can see that our model that we used is underestimating the number of Ebola cases. So that tells you that the continuous growth rate is even higher or larger than the, what was it up here? 1.252%, right? So it's even greater than this rate that was recorded or used as a model for this time period. So that's how you can use exponential growth models. And again, you have the flexibility of using your traditional exponential model with a base that is a number greater than 0, or you can use your continuous growth rate with your base of E. Any questions on this before we move along? No? Okay. All right, let's take a look at, let's see if my other lecture has come in yet. Has it? Yay. So I'm just going to scoot up to, it will still keep recording. I just had some new problems in here that I wanted to show you. All right, so glad it finally did some syncing. So I think we're right here. Yes, okay. So radioactive decay would be an example of exponential decay. And similarly, you have, again, two models you can use. The first model is your typical exponential decay model where your base is a number between 0 and 1. In this case, for half-life, the base is 1/2 because half-life tells us the time required for 1/2 of the current amount of a substance to decay. All right. The continuous, if we have a continuous decay rate, this is the model that we use. So sometimes students say, oh, which one should I use? Well, write them both down on your cheat sheet for your final. And depending on what information you're given, okay, you can use one or the other. And if you have time and you want to check yourself, you could do both, and hopefully you'll get the same answer if you've used them correctly. So let's take a look at what all these different variables mean. M sub naught is acting just like the A sub naught in our model in number 1. It's the initial amount, the initial mass that you have. 1/2 is the number 1/2 for half-life. T is the time, the amount of time that's passed, and H is the half-life. So if you know the half-life, just use this formula. This formula is using E as the base, and R here is the continuous decay rate of the substance. So if you're given the continuous decay rate, you would use this formula. And these two equations are equivalent, and you can make them equivalent by using these substitutions. R is the natural log of 2 over H, and H is the natural log of 2 over R. So let's use both of these models real quick, just do some substitution for this particular problem. The burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it originally contained. Carbon-14 is used to date fossils and, you know, that archaeologists find when they go out in their little digs. And if we are living right now as human beings, we have 100% of carbon-14 in our bodies because we're all alive. As we die, when we die, we start to, the percentage of carbon-14 in our body starts to decrease based on this half-life right here. So to have 50% of the carbon-14 we have right now in our body, 5,730 years will have had to pass. Okay, so you can already get an estimate of your answer. Your answer has to be less than 5,730 years for this Egyptian mummy cloth, burial cloth. Why did I say that? It has to be less than 5,730 years. Chris? Right, because it still contains 59% of the original carbon-14. Right? If it said 50% here, we wouldn't even have to do any work. We could just say, hey, the thing's 5,730 years old. So in a discussion with my earlier class, we talked about, one of my students asked for things that are in the millions of years. And they use another dating method that uses potassium argon dating. And I know nothing about that. We happen to look it up on the internet, which has millions of years. You can look up things that are millions of years old by using that particular dating method. So I'll have to go talk to some of the scientists in the science department and see if they've used any of that or have any examples of it. But half-life and carbon-14 dating is probably the example that you see the most in math classes or in some of your science classes for exponential decay. So let's see if we can use this model right here to figure out how old the mummy is. Now, why am I saying this model here versus this model with E as a base? Why am I choosing this one? Like if you're on a test, why would you use this one? Because why would I say this model is so much easier to use? Yeah, because you know the half-life. So why get involved with doing this kind of calculation for R, okay, which this is supposed to have an R up here. This is negative RT, okay? When you're given the half-life, you know the half-life, so use your model right here. A of T, or let's stick with M of T. I took this off of another lecture, so let's say M of T equals M sub naught times 1/2 to the T divided by the half-life. There it is, 5730. Okay. Well, you still don't have the answer to your problem. You got to figure out how to use the remaining information in the problem to solve this equation. And right now, you have two things you don't know in this equation. We're trying to solve for T. This is what we're trying to solve for. We're trying to solve for T. And right now, you still have M sub naught and you have M of T that are unknown. So you've got to somehow be able to use this information right here to help you solve this equation. And this is probably the first time you see one of these problems. This is the hardest part of the problem. It's just figuring out how to use 59% of the carbon-14 it originally contained and what to do with that. Anybody help us out with that? You were trying to solve this equation, what you would do? Katie, what do you think? Yep, point. Right, M of T represents the mass of the substance remaining at time T. So we're saying right now, when we've unearthed this burial cloth, it had 59% of the original amount of carbon-14. So the original amount is right here, M sub naught. All right, so it's going to be 0.59 times M sub naught, or M sub 0, equals M sub 0 times 1/2 to the T over 5730. So that's really the trickiest part right there. Some students, usually the answer I get is people want to put 0.59 there because they take 59% and they make it 0.59. And I say to students, 0.59 is a percentage. Percentage has no units attached to it. You have units over on this side. You have to have units. The units on the left side have to equal the units on the right side. And if we were talking about a population, the number of people have to equal the number of people. You can't just have a percentage, a decimal sitting out here with no units attached to it. So, yeah. Never mind. Oh, that's just my pen didn't close it very well. Okay, that's a little sub knot. Let me see if I can make it look better. You know, not N-A, how do you spell that? N-A-U-G-H, right? Look, think of my last name. N-A-U-G-H. They used to call college now. All right, so if we're going to solve this for T, right, we divide both sides by M sub naught, and I'm going to move to the other page because I need a little more room. So we get 0.59 equals 1/2 to the T divided by 57, what was it, 30? Okay, so we originally had this. Before I switched pages, my M sub naughts cancel when I divided both sides by M sub naught. And now I still have to solve for T, so I have to use one of my log properties to bring T down. So I can either use the common log, take the common log of both sides, or the natural log. So I'm just going to use the natural log. So my right side is just the natural log of 0.59 equals the natural log of 1/2. And this whole thing just comes right down in front. So it's T over 5730. So that's just a proportion, folks. Okay, so you can either do cross multiplication and set them equal, or you can multiply both sides of this equation by the denominator, which is 5730. So that cancels the 5730 on the right-hand side, and we get 5730 times the natural log of 0.59 is equal to T times the natural log of 1/2. So don't lose track of what you're trying to solve for. You're trying to figure out how long this thing has been buried, t. So t is being multiplied by a number. It happens to be called the natural log of 1/2, but you're not going to let that scare you now. You just divide both sides by the natural log of 1/2. And so t is equal to 5730 times the natural log of 0.59 over the natural log of 1/2. So again, just for you to get a sense, again, remember your natural log function looks like this, and it goes through 1, 0. So since both of these inputs into your natural log is a number, it's a fraction between 0 and 1, both of these natural logs are going to be below the x-axis. They're both going to be negative, but a negative divided by a negative will give you a positive. So I'm just trying to show you that anytime you take the natural log of a number that's between 0 and 1, your answer is going to be negative. You can't have negative times, so both of these are negative here if you look at this graph of your natural log function. So let's figure that out by throwing it into our handy dandy calculator. So we have, and I'm going to put the entire numerator here in parentheses. So we have parentheses 5730 times the natural log of 0.59, two parentheses, divided by the natural log of 1/2. And that gives me 4,361.75 years old. So that's 4,362 roughly. So t is approximately 4362. So if I wrote out a sentence to answer this, that's when I attach the units. T does not have units on it right now. T is just a number. That's a little subtlety that a lot of you miss. You often will put years after when you solve for your variable. T is the number 4362 approximately. Then you say this thing was buried 4,362 years ago if it contains 59% of the original carbon-14. So that's when you actually attach your units. So any questions on solving this equation? Okay, now to find the continuous growth rate, if you were interested, you would have to you'd have to find out R. And again, R is the natural log of 2 divided by H. So R is going to be the natural log of 2 divided by H, which is the natural log of 2 divided by 5730. So that's what you would use. Excuse me? The H looks like an LN. It does? Here? Yeah, R equals the natural log of 2 over H, the half-life. Yep, that's how you solve for R. And again, you can find these values out yourself if you set these two equations equal to each other. You can see how R is equal to the natural log of 2 over 5730. The one hint I would give you if you want to try that on your own is you can represent 1/2 as 2 to the negative 1. And then you'll get to see where that negative comes from over here, if you like to work those things out on your own. Okay, so that's continuous growth, continuous decay. And then your next, in your particular package, you just have this example of a logistic growth. And I came up with, let's see, is this my new one? No. Come on, didn't you come up yet? I have the logistic growth, but I gave you a new example to look at. File and use. Okay, come on, where is it? This isn't it. Nope, that's one we started with. Okay. Cross that one out. Can't find it. Guess it never, oh, there it is. Okay, here we go. I did find it. So logistic growth models, I've referred to this when we were studying population growth, when we were looking at the rabbit utopia problem. In most growth situations, indefinite exponential growth is not realistic. We know that a population can't grow without bound. growth is always limited because of either space resource or food resources. The logistic growth models used to capture the long-term end behavior of a growing population. So let's take a look at this. Notice the blue part of this graph looks just like exponential growth. Okay, so the y-intercept is going to be your original amount or your original population at t equals 0. That's your y-intercept. It's going to grow at some rate, and this point right here represents how long. Right here, that's your maximum growth rate. So you can actually find, like if you're looking at the number of days or the number of weeks, what your population would be at that particular point. And from that point on, your population is still growing, but the rate that it's growing is decreasing. And eventually it approaches long-term behavior. As T gets bigger and bigger and bigger, it's approaching this sort of upper limit here, a limit to the growth. So that's your horizontal asymptote. And the equation for that asymptote is y equals c. And where you find that value of c is in the numerator of your exponential growth model. C represents the term carrying capacity. That's what we call that horizontal limit to growth, is the carrying capacity for a particular population. So let's take a look. I found an example of this because this can look pretty scary when you look at this formula, 1 plus a e to the negative bt. But I want to show you something really quick. If I ask you how many, if whatever this model is representing, what was the initial amount of your population, whether that population was people or the number of wolves in Yellowstone National Park, gray wolves that they've introduced back into Yellowstone, or the number of bacteria in a petri dish, you can get your answer pretty quickly because the initial time is t equals 0. And look what happens to this formula when you look at t equals 0. It's c over 1 plus a to the e times e to the minus b times 0, which is c over 1 plus a times e to the 0. And what's e to the 0 equal? 1. So you can find the initial population size by just dividing these two numbers. Your carrying capacity, which you can always tell by looking, if you had a graph, you can always tell by looking at your horizontal asymptote, which is the end behavior of your graph, that limiting number, and 1 plus a. So you would have a from your model, or you'd have a graph with the equation for your model given. So if I ask you to find the initial number of people or bacteria or gray wolves, you just do c divided by 1 plus a. It pops right out very easily. So let's take a look at a real quick, because I want to give you some time to work on these problems. So here's the mathematical model we were just looking at, and I found a flu virus equation. And it says the spread of a virus through a student population, you're all students. Most of you, some of you have ended up with that stomach virus that was going around 2 or 3 weeks ago. It's modeled by this. So I'm going to call this S of t. S of t equals 5,000 divided by 1 plus 4999 e to the negative 0.8 t. Okay, S is the total number of students infected after t days. How many people were initially infected? How do I find that? That's the y-intercept, where t equals 0. So to find the number of students that were initially infected, all I do, if I use the little formula I just showed you, it's c divided by 1 plus 4999. Because e to the 0 just becomes 1. So that shows you 5,000. This makes sense. There was one student initially with the virus, and then it started spreading. Yeah. A is just a variable that you'll be given when you're actually given the model. And in this case, it's what makes, when you're doing a model, sometimes you can't actually say that it represents this particular number or that particular number. You take all your data and you do a regression. And it's just what pops out of your regression model based on your data. Okay? So this tells you that originally there was one person infected and then it started spreading. What's the most number of people that can be affected by this particular virus? 5,000, that's your top number here. That's your carrying capacity. That's your horizontal asymptote, okay? So the maximum number of students that can be affected in the long term, we've got a contained population here, is 5,000. So this could represent perhaps a university, a small university or a school, and you have a set number of students. So that's 5,000, and that's just the numerator. Okay, that's all you have to do. Yep. Yeah, I mean, remember, you can cross a horizontal asymptote. So you could actually, this, excuse me?
I thought that was with like a different part of the graph. So I didn't know if it's
It could cross it. You could actually reach, all people could get infected. Hopefully not everybody gets infected, right? But so that's why it's just the upper bound, because that's how many students you have. You could actually have everybody get infected with the virus. If you put everybody in one room and you wouldn't allow people to wash their hands or, whatever, right? I mean, we wouldn't want to, that would be what do they call that? Dysutopias, or what do they call it when it's dystopia, right? When it's the opposite. But that would be the maximum number. And yeah, you could actually achieve 5,000. There's nothing mathematically incorrect about actually crossing the horizontal asymptote. It's the vertical asymptote that doesn't make sense, because that's the value of x that would make your denominator 0. Now you can ask questions, and I don't want to take too much more time, but you could also set this equal to say, well, when would I reach 3,000 students, right? You could do this kind of thing. And because you have all your data, and I won't do this for you, but you could solve this problem right here by multiplying both sides of your equation by the denominator and then just using algebra, and then you take the natural log of both sides. So you can start answering questions like that as well. So that's your logistic growth model. You'll be seeing it again. So what I want you to do, and I was going to show you a bacteria growing, but yeah. So here's your first activity. I want you to only spend about 15 minutes on this, and then at 20 of, if you're not there, I'd like you to start problem number 4, which is, oops, I went too far ahead of myself. Problem number 4, which is this particular problem right here that has a logistic growth model. Because you will see a logistic growth model on your final. You'll be asked some questions about it, and I just want you to have some practice with it. Okay, so make sure you come back to this around 10:40. I'll remind you when it's 10:40. Okay, so if you have any questions trying to fill out this activity, just raise your hand and I'll help you. After you fill in this table, then you're going to actually start matching each of these graphs to the particular country that it represents.